Okay, so welcome everyone. I think we're going to start. So it's our great pleasure today to welcome Vincent Danos, who is a Directeur de Recherche at CNRS. Vincent has a long history of research at the interaction of computer science and different fields. One of them is obviously logic at the beginning, but now biology, of course, with kappa and the graph writing that most of you knows by now. Also at the interactions with physics and quantum with measurement calculus. And more recently, Vincent has started to be interested in exchanges, decentralized finance on the blockchain. So he's going to talk today about yet another field that theoretical computer science can start colonizing, which is economy and finance. The link with the GReTA seminar is, so usually we have talks which can be pretty theoretical on graph writing or applied talks. And this time, I think, if I understand, the talk is going to be about potential applications of graph transformation and graph writing, because as we all see, there are many graph and quantitative data that are involved in these decentralized finance schemes. So without further delay, I will let Vincent tell us about decentralized finance. Thank you, Vincent.
Thank you. It's a pleasure to be here. Thank you for your attention. Yeah, maybe I'll start with a little anecdote or a little view on what finance and markets, actually the engines of finance are, which I think will drive us directly into what's so special about decentralized finance. And there are many things that are special about decentralized finance, not just what I'm going to say. So you probably all heard about something called high frequency trading. And if you look at it from far away, what's happening is that people are ready to pay a lot to be able to connect traders, are able to be able to connect the trading strategies to as quickly as possible, as real time as possible to exchanges. So they want to move their orders and update them, cancel them, do all sorts of manipulations of that sort. And they literally pay for renting server space, which is next to the exchange or exchanges, because they usually play on many of them. So in a way, decentralized finance is a way to put your strategy inside the exchange or inside a network of exchanges. And that's what we're going to talk about mostly today. And so in a way, decentralized finance could be seen independently of the blockchain, which is also important for obvious reasons, could be seen as a new substrate where your strategies are programmable, composable, where they access all exchanges at once. And in the atomicity of a series of transactions, you can construct very many totally novel ways to interact with flows of assets and money. Okay, so the way I'm going to structure that presentation is I spend quite a while, maybe up to a third of the talk, not really describing much in terms of results, but more describing how we tend to think about decentralized finance, what's happening there, what are the new objects, independently of the fact that I or with colleagues, we have worked on them, but new objects that may be of interest to computer scientists at large. So a really amusing object of that type, which we're going to look at for 5 minutes, maybe, is price machines, and I'll explain that. And then I'll go a little bit into how those price machines compete with each other and what it means in terms of capital efficiency, which is a kind of obsession of the entire financial system, and on the theory side and on the practice side as well. And then I'll turn to the specific graph-related problems that we have solved and other questions that we like to solve in the future. All right, so let's start. So what's decentralized finance? Some kind of open finance And what's a TriState machine? I'll give you a little, I think, a short and crisp presentation of a TriState machine. But here I must say, as computer scientists, you'll find that that question, what is it abstractly, is not completely answered yet. And that's actually quite an interesting line of investigation. But then most of the talk will be about not just one price machine, but a bunch of connected price machines. And we'll ask global graph related questions about that object. And so the questions have names, so I can tell you right away. We'll define them carefully. Actually, most of the contribution is defining those questions. So there's the arbitrage question and there's the order routing questions. And I also talk about competition for liquidity in the absence of what people call the lender of last resort. So essentially, there's something very special about DeFi, about the monetary mass, which is that it's not infinite or unbounded. It's actually finite. It's managed by tiny little smart contracts that are called ERC20s. And that single constraint actually propagates to the entire system. Okay, so we'll talk about that as well. Yeah, so introduction to decentralized finance. So first of all, it touches on multiple subjects. So it's a bit hard to wrap one's mind around it. There's economics and finance, mathematical finance, the mathematics of market microstructure. So how exactly is a price computed? What's the auction mechanism that's underpinning most markets or the price machines, kind of invention from decentralized finance. Then there are economic/computer science questions around mechanism designs and how you should best design continuous actions. And there's an amazing variety of little, what people call trading rules. And in that diversity hides a lot of really interesting questions. I'll give you just one for reference. If you place an order somewhere and I come after you and I want to place a different volume but same price, so we're on the same price tick, so people say, then now if we are matched by the engine, meaning some taker wants to take either of, because it's completely equivalent to the taker, which of the two orders you should take, because there's the same price, right? So should we do it first in, first out style, FIFO, like, okay, or a stack maybe, or should we do proportional allocation? So, you know, regardless of when I arrived and I may be late in the game, but there's no queuing mechanism, will be served to the, in proportion to the volume we're serving. And as soon as you enter this, this kind of question, there's a design space which is huge, and you know, that people are trying to understand. So this is this kind of middle territory of questions, and then there is purely computer science questions, obviously, distributed systems, composability, process communication, all that's familiar to us. So one thing that makes me and other people in the field interested in this new set of questions, at least new to us, is that I think there's an interesting opportunity if you like this kind of thing. So there's today little distance between ID, paper, product, and that's not always true in the many provinces of science, right? And because of that, there is also a strong and super creative entrainment from the industry on the research. So you see amazing papers that may not be quite to the format we expect in academia, but nevertheless, there are real contributions. They are really opening new avenues, and that they come from the industry. So there's that's quite an exciting intellectual adventure, I would say, just starting, really. And I don't know if you know, but today in the Financial Times, there are 10 articles a day on decentralized finance. I mean, it's no longer like a niche exercise of geekish people. And by the way, talking about geeks, they already changed the world, maybe not for the better in the 90s by programming Amazon and Facebook and stuff like this. So if you want that kind of reference, what's happening in decentralized finance is that now you're 17 years old, something a bit bored during the holidays, and you've been, betting online, playing poker or whatever, you get interested, you get involved, and next thing you know, you have built a bank, an exchange, a lending machine. You've rebuilt on-chain financial functionalities, a little piece maybe of things that are bundled usually in the banking system, and it's a completely open game. So that in itself has the potential to change a lot the game. And it's not easy to change the game of finance, right? It's got it's 10% of the GDP, of the planetary GDP, and it's not changed that much over the last 4 centuries. And also, like I said, not just in the financial times, you see clearly that traditional finance has run out of ideas, is strangled by regulations, and it's moving, the people, the money is moving to centralized finance for crypto, and then to decentralized finance. And there are names of exchanges that come straight from that traditional world. So the object of interest mostly for that talk is a huge graph. So on the right-hand side, you have a tiny view of a very special subset of that graph. So we're going to take 5 minutes to explain this. So I'll tell you how I built that graph. So we went to the blockchain, which archives everything, right? It's Ethereum, actually, I should have said. So it's not any blockchain at the moment. Ethereum is mostly where the action is in terms of decentralized finance. And we picked up the 64 top assets in terms of market cap at the end of 2020. So these are the nodes that you see around. They're color-coded a little bit. There are bright red ones. I'll come to it in a second. You see they have a much higher degree than the others. So they feel more like cash, whereas the other nodes feel more like maybe stock or something. So, but computer science-wise, they're all ERC20, so they're tokens. And what's an ERC20, if you don't know, it's a tiny smart contract that essentially maps a bunch of addresses to a bunch of amounts of something. And that something is a token, and the token's definition and properties is exactly summarized by the ERC20. So it's a mini machine that traces who owns which amount of what. And there's one per every ERC20. It's quite normalized, and it's part of the basic layer of the protocol that makes this finance so different from the original one, because it's all at the same place, using the same language, and using the same communication structure. Okay, so now we like graphs, we like edges. So what's an edge on this graph? It's a specific type of smart contract, which is a little more evolved, and it's in charge of giving people who wish to do so means to exchange one of the two ends. So a certain amount of, let's say we have an edge between token A and token B. That edge, in a way or another, and there are many implementations, will give people who want to the ability to sell a certain amount of A's in return to a certain number of B's. And so depending on whether the edge is based on, like traditional markets, on an auction, or on a continuous auction, also called an order book, or on a price machine, as I will describe next, the process by which you compute the amount of B's you get for a certain given amount of A's, that's going to vary. But in general, we put an edge between two nodes in our mental model if there is a way to directly exchange A's for B's and B's for A's. Usually those connections are bidirectional. So essentially, decentralized finance is nothing else but this graph with a great variety of means to connect two nodes. You also have hyper edges, but they all called balancer, and we can discuss the details, but it's essentially a large graph that's growing autonomously, like the web used to do in the 90s. And that large graph has essentially, in that large graph, edges or hyper edges have essentially two functionalities that are quite distinct. One is to exchange reversibly, and the other one is to exchange irreversibly. So irreversibly, it's called spot market. It means I come into the edge, I give us a number of A's, I get us a number of B's, and that's that. It's finished. It's an instantaneous interaction with the graph. So, and if I'm doing a reversible swap or a repurchase agreement or a credit line, it goes under so many names, secured lending machines, I put a certain amount of A's, I borrow a certain number of B's, and I have the option, depending on the conditions, to buy back the A's I put with a certain amount of B's, usually a bit larger than what I borrowed because of the mechanism of interest rates. So this is it. This is decentralized finance, in a way, described technically. And here, that particular graph is based on irreversible swaps and very specific TriState machines of the Uniswap type. And they are the dominant form of exchanges on Ethereum at the moment, although it's being a little contested. It was not always the case, and it's really interesting. And really, they are computer sciencey objects. They are just pure automata. The only difference is that their state codes for reserves of assets, and their transitions, as we will see in a second, are just coding for moving these assets around in the respective ERC20s. So now, that object we're looking at is by no means the total graph, right? So this is just a tiny object that we built from data. The real graph has tens of thousands of nodes and edges, and there are in between two nodes, you may have dozens of different types of edges that are competing, that are offering you different ways to exchange A with B's. So every tiny edge is an exchange platform, either reversible or irreversible, and you have just so many of them. To be fair, there's a lot more complexity on the irreversible exchanges, which is kind of the simplest kind of transaction, because the reversible ones, as the name suggests, they have to track down something about the history. Their output is not simple. It's a process. It's extended in time, and it's a lot more bother to manage, and you have far fewer of them. All right, so that's decentralized finance to us. And now I'm going to explain quickly what's a TriState machine. I'll take an example. So a TriState machine of the simplest type, okay? So the Uniswap type. So the funny thing is that so the functionality is clear, right? It should let anyone come with a certain number of A's and get B's in return, and conversely. Now, the entire question is, how do you do that? How do you compute the price? How do you know the price? So the traditional financial answer to this is, let's make an auction, or let's make a continuous auction. That's called the order book. So people propose a certain volume of B's for a certain volume of A's, or at a certain price. And on the other side of the book, they propose the other thing, symmetric thing, and that's called a resting offer. And then when people want to swap, they pick up the best one they can, or more to the point, there is a matching engine that's going to automatically execute in the best possible way, starting with the best price and then the second best price, and so on and so forth, and until the volume of the order, the market order, is completely filled. So that's easy. This is not what's happening in decentralized finance at the moment. Instead, there is no auction mechanism. Instead, there are two categories of people. So you still see the dichotomy between the people who provide liquidity that we call liquidity providers, LPs. I know there is a little trick here to annotate. So let me do this. Yeah, do that. So LPs, this stands for liquidity providers. So these are the people, just like in the traditional auction, people who offer something. So they say, I'm ready to do this. So there are people who come first, if you wish. And then there are the other guys who are the liquidity consumers. And what these people do is they come and take the liquidity that was offered by the other population. The two subpopulation, LPs and LCs, can intersect, of course, if you look at the agent. But it's a good dichotomy to keep in mind. And in economics terms, that's what people call a two-sided market. So you really have two different types of users. And if you want to make them interesting and interacting with you, you have to please both sides. And, huge amount of literature on the subject. So there's still the same LC-LP asymmetry in the case of TriState Machines, but it plays out differently because the liquidity providers, they do not compete with each other. They're not trying to ask for less than one than the other to be the first to be taken. They're pooling their liquidity, which they deposit in what's called reserves, which are managed by the TriState machine. So the TriState machine at any given time has a certain stock of A's and a certain stock of B's, and it's going to pay out B's for A's or A's for B's depending on that stock. So just like an ordinary state machine, but it's moving assets, so something with value. So let's see how it works. I'm going to give you a real simple but rather complete description for the Uniswap TriState machine. So here, this axis is the amount of A's that are inside the state machine, so to speak. So you have these two buckets or these two reserves. Technically, of course, it's just some kind of state of the ERC20s, but let's be a little more abstract. So you're the machine, you have A's and B's. And so some kind of point here in this plane indicates the state of your reserves. That's your state. So you have to think of this diagram as being drawn in log space. So I'm actually tracking the log of the number of A's you have and the log of the number of B's. Now you can have two types of transitions. You have the blue transitions for liquidity providers and the red transitions for the liquidity consumers. So let's start with the liquidity consumers. So like we said, if you're a liquidity consumer, you can enter the contract with A's and exit with B's, or you can do the opposite. So in log space, the Uniswap TriState machine allows you to draw any vector here. So you see that you're giving away A's here, and then you are giving and you are injecting B's, because there will be more B's at the end of the transition. So I guess I got it wrong, because you're swapping B's for A's. And so from the point of view of the outsider who's consuming, you deposit B's, which means that the Y coordinate goes up, and you withdraw A's, which means that the A coordinate goes down. So sorry, it's swap B's for A's here. And whatever the direction, it's based on the same principle. The price is computed in a way that you stay on this simplex here, which is in log space just means that log A plus log B should be a constant. So in normal space, it's called constant product TriState machine. And that's what Uniswap is. So that tells you in a given state and given a certain amount of B's that you receive, how many A's you're going to give away to the liquidity consumer. And it's got a beautiful little property, which makes sense in general, which is that you can never dry up your reserves completely, because in that space there will you will be asymptotically at least -1 or just above, and which corresponds in the normal space into never being completely dry. And okay, and in that same space, if you're a liquidity provider, then you're going to use the blue vectors. So if you increase both coordinates, this means you're depositing. And if you decrease both, this means you're withdrawing. And of course, withdrawing can only be done if you have a share of the pool, which the contract keeps track of, obviously. And what's the rule for depositing? It's very simple. It's that this time, your vector should be parallel to the bisecting line, which means you have to provide equal proportions of A's and B's. And if you think of it a second, this has a nice property that the price, which is the zero derivative of this pricing function, which is implicit in this diagram, will not change if you withdraw or deposit. So the infinitesimal price of A's for B's stays the same under the action of liquidity providers. Okay, so that's the description of the simplest TriState machines. And let it be clear, if you don't know the field, that this has been generalized to, n assets with, so more like with hyper edges and in all sorts of ways and quite clever ways. But the basic principle is this one. And if you're an economist or if you're interested in this matter, what's most remarkable about this mechanism is that there's no price defined by any competitive process. So essentially, what's happening here is that the proper price, which is this zero derivative we're talking about, is set up by people who know the price somewhere else and come and arbitrage the system. And so we'll talk about arbitrage in a second. Right. So I have to do something here, I think. Yep. Oops. And also I probably have to clear up something here. Give me a second. Clear my drawings. Yeah, good. All right, so let's return to the graph itself. So this Uniswap graph, if I can. Yeah, so here I'm taking a detail, and what you see here is a little high degree node, which is a stable coin. And that's so Ethereum has what's a stable coin? It's a projection of a known fiat from the outer world, the off-chain world. So here it's the US dollar. And you see that it's like cash indeed in the graph theoretic sense that it's a really high degree node. So this is one kind of operational definition of cash. You can buy lots of things with cash, but things that are less cash, for example, here you have the degree 2 nodes. Those guys are less exchangeable. So there's so this is to say that the graph, which by the way is not just much larger, but also changing all the time in a decentralized way, that graph is very heterogeneous in terms of degree distribution. So, and it's far from complete. It's a bit like the web. And this is so since most of these edges are TriState machines, you can ask what's the total value which is locked in all the edges. And the last time I checked, it was 70 billion US dollar. So it's a visible amount of value, which is caught in a very heterogeneous way in this graph. So what's so special about this graph? There's no custody, so no one is actually taking care of your money. You don't have to trust anything. It's purely based on code. There's free entry. It's completely organic, the growth. Most of the existing price machines are based on reserves, so they lock their liquidities. That generates intense competition for liquidity, because if you build a new exchange, like a new little edge on that graph, you have to provide liquidity, and you have to be, make some kind of incentive system to get that liquidity from the people who have it. But I think by and large, the most interesting aspect for us, at least, is that this is a world which is completely composable. So this is a tiny little piece of data that I give you. You see, so it may not be explicit in the representation I chose to present the TriState machines, but those TriState machines are very concave price functions, meaning that the infinitesimal price, so the amount of B's you receive for a very small amount of A's, so the ratio between the two, which you can call the price if you want, which is just the derivative at zero of the price function, that price goes away from you very quickly when you ask more volume. And here I'm showing you actual data, which shows that most of the orders that are executed on those edges that we presented are under 1% of the relative size of the reserves. So meaning if you have 100 million US dollar, in the reserves, then no one ever orders more than $1 million swap. And this is because of concavity. And this is very inefficient, because it means that 99% of the capital that's actually trapped in the edge is just sitting there in an idle way, generating nothing, no good for anyone, and never being used. So that's a tension in the space at the moment. So composability is something I'd like to give you an example for. We're going to interpret, or on an example, right? The concrete example, the ability for anyone to be able to write a new contract, the ability to introduce a contract that's going to do things, new functionalities that rely on existing functionalities and that rely essentially on the ability that of the new contract we're writing to generate call on pre-existing contracts. So let's do this. I'm going to pick up my annotation tool again. So I'm going to assume that in the system there's a repo machine, a lending machine, so a reversible swap machine. And here I'm a dealer or I'm a market maker, and what I don't like to do, so I'm willing to buy and sell all the time. So sell A's for B's or sell B's for A's, let's say. And what I'm trying to avoid is to have to lock up the liquidity that I'm selling in the system. So I'm going to write a specific contract. And of course, many dealers could actually subscribe to this mechanism, but let's say there's just one here. And the contract will do the following. When a seller shows up, so it's fundamental here that the seller actually reads the code and can actually be confident that whatever is going to do whatever asset is going to inject in that code is going to be handled in a way that's completely predictable. So this is the blockchain effect, if you want. So seller has done his homework and he knows that the code is correct. So he knows the functionality. So without any more trusting issues, he's going to send a certain amount of asset to this contract saying he wants to get the other type of asset. So this is going to work like a swap mechanism. So what's the dealer going to do? It has two sources of, let me erase all this. It's got two sources of assets. A certain quantity here, which he owns, which is its pre-financing part, and a certain amount of assets that have just been given flash length, is what people say, by the seller. And atomically, the following will happen. It will join the two sources of liquidity here. Then it will use that joint amount of capital as collateral. So it will go to the pawn shop atomically and say, okay, this is what I deposit and give me a certain amount of things that I can borrow. And everything is computed in a way that the amount you can borrow is exactly what the seller was promised in the first place. And then the seller exits the game. And for all that matters, it's by similar, completely invisible that some kind of atomic little manipulation, commutation, we would say, between having something and selling it happen. So here, the dealer actually managed this kind of time paradox, which is to borrow using, by gauging something, depositing something that he actually has not paid for yet, right? Because what you take the money of the taker, you deposit it, and after that, based on that deposit, you can borrow the cash, which is enough to pay the seller. So this is a beautiful little commuting of steps, which is possible because of the atomicity of the transactions. And if this is also the reason why you have to pick up the code. And on the other side, it's exactly the same mechanism. And what this mechanism does for you, it allows you to be active on a market with no capital, essentially. And how did we get this? Module the fact that you need the users, of course, and you need to tell the users. But how do we do this? Just by programming a tiny piece of code, which is maybe 100 lines of solidity, and connecting it to an open repo machine that, willing or not, is going to help us realize this strategy. So that, I think, should give you the essence of why simple composability in the protocol, in that environment where people manipulate value, is a huge deal and has a tremendous impact. And this is exactly what traditional finance doesn't have. I mean, there are other differences. I don't want, but this one seems to us the most interesting one. Okay, so think I have to do something here. Sorry, I'm a bit new to this annotation thing. Is that, yeah, cool. All right. Composability, I give you another example where you can do fractional liquidity, which is also called ghost liquidity, something that financial markets, traditional ones, I mean, kind of have an ambiguous relationship to. They love it, but they hate it. It looks evil, but it looks very efficient, and they don't quite know what to do with it. But in the context where we are, DeFi, it's actually quite obvious you can do it. And it pumps up the efficiency of your liquidity very much. I mean, you have to realize, all of you, this is all trivial from the computer science point of view. It's like distributed system and atomic transaction stuff, which we learn about as undergrads for the most lucky of us. But it completely changes the game because people are moving money. So somehow this DeFi is like CS 101 meets with exchanges and financial mechanisms. And I'm not saying here the fact that it didn't happen before has nothing to do with the fact that people didn't know about it. It's all to do with the fact that the institutions don't want it to happen for obvious reasons. So anyway, what here you're doing, you have a little vault with a certain amount of A's that you're at your disposal. And maybe this is playing out on some kind of side chain. You don't have to be on the main chain. And you're connecting the same amount of liquidity to, let's say, 3 different exchanges. So you're ready to exchange A against B1, B2, B3, let's say. And here's the trick. What you're going to do is you're going to have a resting offer on all these structures. The mode you're actually using doesn't matter whether it's an AMM or something else. As long as you can use this composability trick, you're going to display 3 times the amount of liquidity you actually have. But since the execution is completely sequential, let's say you are taken on that market, your little strategy will maybe volume adjust both of these and say, okay, I don't have that much volume anymore, or maybe cancel completely the order. And so what have you done? In effect, you have amplified the rate at which you're trading by a kind of a magic effect, which is, simple programming. So composability example 1 was about commuting, buying and paying for what you buy. And here it's about commuting, or it's more like about conflict. If you think with your rewriting system cap, is the ability to escape to live atomically with possibly conflicting events. And when one event conflicting with another has happened, then you just cancel the ability of the other event to happen. And of course, this is possible only because you're in a completely sequential model. All right, so this is, I think, should be good enough to explain why composability is such a big deal. And then I do now a bit of generic remarks about the different types of blockchains. So here I decided to represent, for what it's worth, the characteristics of the substrate blockchain along 2 dimensions. So there's that dimension, which is the time scale, the smallest time scale at which your blockchain operates. So you have to understand that you are measuring yourself against off-chain finance. So centralized exchanges like Binance and Kraken and Coinbase and whatnot. And those guys, they operate, like ordinary markets at the, well under a second time scale. But since there is this block generating mechanism on the blockchain on Ethereum, this is, once every 10 seconds. So the least delta T that you can actually operate at is orders of magnitude different. So there is that lag. So as you go up here, you have a, let's say, a slower chain. And when you go along the other axis, you have a more expensive chain. And this is, so at the moment, Ethereum can get super congested. And so running this tiny little contracts, borrowing and depositing and all that stuff can become dissuasively expensive. And so it's really important when you gauge how profitable your strategy may be, that you keep in mind how expensive it can be to maintain. And the two dimensions kind of join forces to make your life difficult, because the larger the timescale gap, the more effort you have to make to keep whatever your contract is doing abreast of what the price processes are in the real world, and the more it costs you in terms of gas price. So let me introduce you to the concept of layer 2. So there's one which is quite fashionable at the moment, which is Polygon, formerly known as Matic. There is also optimism that we discussed with Cesar a few weeks ago. So there are all sorts of zero knowledge based type of sidechain, parachain, layer 2s. All these are all vaguely synonymous from the point of view of that talk. And they all promise the same thing, which is to manage, to bring down the operational expenses a lot. And so therefore, to free up the design space in a way that that people can actually bring not just ideas of strategies, but actually finance these ideas of strategies and deploy them in a way that makes sense economically. So one exploiting composability, you can do no provision, which is what we saw with the example number 1. You can also do fractional liquidity, which was example number 2. There are other things that I didn't have time to talk about, but which are related to what people call last look. So the ability to renege on the transaction. So you offer something, and then by the time you're matched, you say, well, I don't want, well, you don't say, the script or the piece of code says, I don't want to do this anymore. This is already existing in Forex exchanges. It also exists in the Chicago Mercantile Exchange, and it's called non-firm quote. So you make an offer with price improvement, which is hilarious. So this is traditional finance we're talking about. So you place an offer, you say, I'm willing to sell that much of this at that price. And then when you're matched, you say, well, maybe I'll sell it a little more, right? You're going to price improve. I don't know. So this gives you an idea of how varied the trading rules can be. And but the point here is that the conceptual point is that the strategic space that you're opening by being composable and by having lots of little DeFi bricks that you can access, that space will be, the usage of that space will depend a lot on these two dimensions. So depend on the substrate blockchains. So not everything is possible everywhere, for sure. So the promise of scalability, if you recontextualize in just the financial applications, is that there will be more intelligence on chain. And so you'll get closer to the dream, as I was saying at the beginning of the talk, which is to really push your strategies, not just very close to the exchange or the exchanges, but inside the exchanges with no limitation on the level of complexity that you can expect to run on the chain. Okay, there are many things to say, but I think I'll stop there. So let's return to the network of TriState Machines and other means of exchanges. So there are general questions about that network that are all very natural. So how does it grow? So this is completely decentralized. You essentially press a button and create new instances of ERC20s or of TriState Machines that you connect. You have to provide liquidity and off you go, which is extraordinary, because if you have a token that you define which is related to a project, then you can make it liquid instantly at a very low cost. And this means that you're entering a new territory for what people call corporate finance or project financing. So this started with ICOs, but it's still growing on strong and based on this complete openness. Another question is who controls that thing? What kind of competition does it generate? Can we come up with profit models? So, And there's also a broad question, which is where the values of the asset come from. I'm not going to get into this one, but I want to ask, which is a very interesting question, where we know some stuff, but it's not for this talk. What I like to concentrate on now is a very global question, which is this price system, which is implied by all these little edges with their reserves or whatnot, is it consistent? And this is the arbitrage question. So, and you know, if you do the arbitrage question, you also solve the routing problem. So let me introduce you to the routing problem on this kind of networks. So I'm asking a question which is rather natural economically or financially, which is I have 100 ETH, and what's the max amount of DAI? DAI is another stable coin, another token. What's the max amount of DAI in a given state of the universe of exchanges? So I snapshot the graph, I look at it, what's the max amount of DAI that I can actually expect to obtain for the input amount in ETH? And I'm allowing myself to use all those automated market makers or TriState machines and all the other means of exchanges. So in other words, all the edges on this huge network. And here is an example of an answer that you get from, this is a price aggregating problem, familiar from online shopping in the 90s, except that it plays out in a very different universe. And this is the kind of answer you get. So let's look at it because it's fun. So you start with ETH, and you see that, so you split your 100 tokens into tiny fractions, and you're going to push them along different paths. And what's interesting is that it's not even true that all the paths that you're going to select on the graph are the shortest ones. Here, you're going to go through, for free, for the top, for the bottom 3 paths, you go through a first step, which is to exchange against another representation of the dollar, and then you go to DAI. So you don't always take the shortest path. And you actually, the optimal routing is a convex combination of something, let's say paths towards the goal that you set. So the input is the starting point, the amount, and the output is this thing. And you're trying to maximize what you get out. So this is the kind of answer you get. So we like to, and it's not even true that it's a set of independent paths. So the support of your optimal strategy can be this kind of entire subgraph. So we're going to model this briefly soon, as soon as I clear my drawings. And this is what I have to do, actually. Okay. So first of all, we have to represent the fact that there is some kind of price machine hiding in every edge. Now, we don't want to be hanging on the details of any particular price machine, so let's define it axiomatically. And so what's a price function? It's a map that's mapping non-negative reals to non-negative ones. If you give it 0 of A, it will return 0 of B, right? Seems reasonable. It's monotonically increasing because if you give me more A's, I will give me more B's. All the edges are behaving like this, obviously, and it's actually strictly increasing. It's strictly concave, so that may be less obvious, which means that, okay, so you give me that much A's, I return that much B's. You give me yet a little more of A's, then you'll get more B's, but less so, not proportionally compared to what you got before. So the higher the volume, the more expensive the mean price you're paying for that volume. So that's concave and strictly seems a good assumption, and it simplifies the math. So we're going to say this, bounded. So that's very natural because you saw that all these little machines rely on liquidity that's actually there, that's locked in the system, or even if there were order books. So bounded just represents the fact that you have only access to a limited mass of tokens, so you can't go to infinity. And actually, this is, there's a broader constraint that I was saying at the beginning, which is that the mass of every single token is fixed mostly for C20s. So you have this at any given time, there's a finite mass, and that's that. Whatever you do, you won't have more than that. And continuous because it's a bit simpler. So what's the model of the situation? It's a graph. The vertices are the RC20s. We don't have loops. It's not simple. It's a multi-graph because there are many, as you've seen in the preceding slide, there are many ways. Then we fix a chosen orientation for each edge, which is going to be a restriction of the type of solutions we're looking for. And the reason we're doing this is because this is a joint work with people I mentioned at the end. The reason we're doing this is not because it's not a restriction, it's because it's a restriction that makes the mathematics work. There are plenty of questions that are yet to explore yet, so this is definitely a weakness, if you wish, in our result. And then we attach to every edge a price function. And you're allowed to take the edge only in the direction that's imposed to you. And then you have this price function. Okay, so now this is the static structure you're working with because the time is frozen. And then you want to say what's your strategic space to route or arbitrage, as we'll see later. So we call this a transfer plan. And it's just simply a map from every edge of the graph. Probably most of the edges will receive 0 to non-negative reals. And so this is a cone, it's the canonical cone actually of dimension E. And so this is a convex subset and it's already a good start of the all possible plans. And this is good for optimization. And we'll say the support of a transfer plan is the subset of the edges where you actually input something. So what do you map an edge to? The edge is directed, you map an edge to the amount of token, which is the source of that edge that you're ready to spend to finance your transfer plan. And then you can derive the profit map directly. So the profit map has two, so the profit map takes as an input, maps the cone of transfer plans to the cone of deltas of wealth, if you want. So this is the V-indexed cone. It's actually a vector space in this case. You map for every token that exists in your model, you map it to the amount by which your wealth varies once you've executed your plan. So we can explain exactly how this function works. So you pick up a transfer plan, psi, which you apply your profit function, psi of tau, then you feed it a certain token, A, and this will return the variation of the amount of A's that you have if you execute the plan. So it has two components, the positive one and the negative one. The positive one is what you'll be given by the price functions, and the negative one is what you'll spend. So we can, they are formulated in the same way. So let's look at the negative one. Maybe I'll take my little annotation tool again. So what you do is you look at all the edges that that A is a source of in your plan, and for all of them you add up the amount of you've invested, essentially the amount of A's you invested in each particular outgoing edge of A, and that's what you spend at A. And conversely, you sum over all the edges that are incoming to node A, and what you receive here is the price function applied to what you put according to your transfer plan at the source of your edge E. So now the good, okay, so this is simple. Now that function is concave and not strictly concave, but something like strictly concave, restricted to the support of tau. And so this is the premise that every problem that you can reasonably articulate that depends on profit as an optimization problem, because of all the assumptions here, will have a unique, well-defined solution. Okay, so let's look at the type of problem we're interested in. So we're interested in routing, as we said. So here's how we can model this thing. You pick up an A and a B, and a quantity small a of A's, and you're trying to max the output over all possible transfer plans, the output of your profit function at B, under the constraints that you don't spend at A more than what your budget allows you to transfer, and everywhere else, well, everywhere else your balance should be positive. And it's easy to see that everywhere else which is connected to B since you're trying to maximize the output at B, your balance will actually be 0, because it's always advantageous because of the assumptions to actually push the potential excess of C through a path to B to get a better result for the objective function, which is here only looking at how much Bs you get out of the system. And that gives you this kind of stuff we were looking at earlier. You can define a subconvex problem based on the independent paths. It's actually quite interesting, but I will skip this. So now we can also do arbitrage. So what's arbitrage? Arbitrage is you pick up an A somewhere and you say, is there any way I can make more A's out of nothing? And this is the consistency problem if you're an economist, right? So is the price system that I'm looking at consistent? So the way to answer the question is to try to make money, right? So the constraint is you'll never spend anything on the balance. You can invest, but then you'll have your transfer plan will generate more profit than losses everywhere. And then you like to have as a consequence, as much A's as you can. So of course, there is always a trivial solution, which is the solution of having the 0 transfer plan. You spend nothing, F0 is 0, so you get nothing. But this is good because it means that you have a feasible set. You have a set of input to the problem, which is not empty. And on the completely abstract conditions, you can prove that that problem has always a unique solution. So there's a best transfer plan. You can prove that once you've executed the transfer plan, which by the way translates directly into a bunch of transactions on Ethereum, right? It says the model is very close to a reality here. You can prove that once you've done it, it's idempotent. There is no new arbitrage. I mean, the next best arbitrage is the 0 arbitrage. You can, if you have differentiable price functions, you can give a combinatorial, you can compute the Jacobian of the profit function psi, and you can derive a necessary and sufficient condition for the existence of an arbitrage, which is proposition 2. And so here it looks a bit too good to be true, but what's happening is that even if that criterion tells you there is a non-zero arbitrage, it absolutely doesn't tell you how large it will be. Maybe it's 10 to the minus 10 A's that you can get in this way, and it's not very interesting. And if you project this kind of proposition on the concrete structure, you get the combinatorial form of this arbitrage necessary and sufficient condition, which you can solve for concrete problems. For example, you can decide that you restrict the support of your plan to simple cycles. So just like independent paths was a subconvex problem of the original routing problem, arbitraging on simple cycles is a subconvex problem technically, which will give you a lower bound on the amount you can achieve on the big problem, but which is much easier to solve. And then you get this, maybe we should just spend 10 seconds on this formula. So this is the corollary written for cyclic arbitrage. And what you see is perhaps not very surprising is that that condition exactly says that you have a non-zero cyclic arbitrage along a cycle if the product of the derivatives at 0, which you encounter of all the price functions you encounter on the cycle, is actually bigger than 1. And that also tells you that you can arbitrage only in one direction. So because they can be both bigger than 1. All right, so that's kind of an accelerated version of our contribution to the problem. We also have explicit closed formula if you specialize the network to this TriState machines of the Uniswap type that I described. And you can also work on the data and look at, with hindsight, at what the opportunities of arbitrage were in the past, which is kind of fun. And I finish with a funny story. So we did all this, and then we met a group in Switzerland at ETH, which was working on exactly the same problem, but instead of computing and then checking with past data, what they did is that they looked at the syntax of patterns of cyclic arbitrage. So it's quite easy when you read through the blockchain to find those kind of patterns, because they're like someone spends A to get B's, then B's to get C's, then C's to get back A's. The cycles can be longer actually, but most of the arbitrage opportunities that have been realized are actually triangular, but sometimes you get more steps. And so the amount of arbitrage that we computed should be an upper bound to the amount of arbitrage that they computed, because we computed all what was possible and they computed all what actually happened. But we were a bit of a bunch of idiots, because we restricted to the most liquid tokens, whereas they did everything. And of course, they found much more arbitrage on the non-liquid tokens, the low volume tokens, than we found on the large market cap tokens. So anyway, it was funny because for a little while, I wasn't understanding why they were finding so much more potential actual revenues, whereas we are computing potential revenues. All right, so sorry, this is the so conclusion of that talk, and maybe after that we can. I'm going to erase these ugly things. So conclusion is we have defined a new object. Composability is really an interesting new primitive. There's the promise of something new, and that's not happening every day in finance. There's interest from finance, actually, a growing interest, but it's still very fragmented and complex. It generates this TriState Machines generates dynamics of competition that it's another talk, but that may not be very stable. It's super capital inefficient. And although composability gives you solutions to this, they are not yet out there. And it's pretty unfair in the sense that we didn't really talk about it, but the asynchrony of talking to the blockchain induces the fact that the some form of front-running opportunity that's highly exploited now, and the system has not really found a good answer for this, but it's super creative, and composability and optimization can help a big deal with this problem. And that was the talk. Thank you for your attention.
Thank you very much, Vincent. So we can all virtually clap. I guess if there's any question, now is a good time to ask, either in the chat or live. Any question? So maybe while people are warming up, if they have questions, Vincent, so the arbitrage you were describing, it looks very reminiscent to the problem of a thermodynamic equilibrium when you have a cycle. So which biologists tend to consider quite a lot when they have these metabolic circles. Is there any formal relation between that and arbitrage?
So yeah, I mean, so in thermodynamics of chemical networks, you have some kind of kinetics, right? So you have some kind of model behind. Even if you're writing graphs or stochastic rewriting, you have some notion of rates, and so you generate events in a way that's kind of a little unstrategic. So no one is really thinking. Molecules just collide in a kind of a stupid way, right? And maybe biological systems have found ways to build compartments and all that stuff. But essentially, the way we describe the situation is that we find the system as it is, and it's got this internal stochastic dynamics, which is essentially the outcome of purely random forces in the system. Here, it's so some of the TriState machines are you can think of them as little chemical reactions for sure, but that's how we describe them actually. But there are two different things. First of all, their stoichiometry is not constant. This is this TriState machine. So the amount of A's you get for your B's is not a constant, depends on the internal state of the system. So it's a kind of varying stoichiometry chemistry in a way, which is fun. And also, I think a major difference is that there are no kinetics. So you have to be an economist and ask yourself. So we can actually replace kinetics by economics. So this is a fantastic question actually. So let me return to my little routing. Not that I'm surprised. It sounds like I'm surprised. So this is the kinetics of decentralized finance. So what you say is, okay, let there be a liquidity consumer and let that guy have a certain amount A of A's. What is he going to do? So this replaces the idea of let there be a molecule and let there be a lot of other molecules. What is it going to collide into? And the fact that there's a unique optimal answer to the optimal routing problem means that if you believe the guy is rational and has all the infrastructure needed to do that calculation, we already know what he's going to do. So we have completely determinized somehow the behavior of the liquidity consumer in that game. And now we can ask questions, that we have the kinetics, if you want. Then we have to postulate some sort of order flow, but we know how it will be dispatched, split over the graph, thanks to this problem. So to the extent that you can describe a bit more, so get rid of some of the complete non-determinism of what people are doing by rational arguments, you get some kind of conceptually, some kind of kinetics, and then you can get a little closer to chemical thermodynamics. So that's interesting. There are other ways in which you can connect because, so we didn't talk about this, but there's a kind of a cognitive scandal in this field, which is that people have defined hundreds of different TriState machines, but there is not, and people have written very convincing proofs of specific properties for these TriState machines, but no one has given an axiomatic definition of comparable to the one I was giving for price function, which is a much easier problem, an axiomatic definition of what's a consistent TriState machine, locally consistent. So there is some kind of, and again, this is a bit reminiscent of thermodynamic cycles and so I can write wrong TriState machines, I give them to you, you don't have a tool to check whether they are correct or not. After a while, you'll see, if I see this, I can pump out all the liquidity. But then what is the abstract definition of being a consistent TriState machine? So that should also be a little bit chemical and thermodynamical in spirit.
So we have a couple of questions in the chat, which I'll read out loud so that the YouTube followers can see it or hear it. So Barbara Koenig is asking the counter of each question, actually. Can linear programming, simplex, help solve the optimization problems, or this beyond what linear programming can do?
It's convex programming, so it's a beyond, but it's well understood how you can do it. So yeah, you can solve those problems. I'm told, because I'm not a convex optimization person, that you can solve, that's probably what the price aggregators are doing, by the way. 1inch, the price aggregator I was talking about a bit earlier. So yeah, it's not linear programming, but it's the next best thing, which is convex programming. So the reason why there are good solutions to those problems is also the reasons why they are quite easy to solve. And interestingly, you can embed those optimizer on chain. So this is maybe worth spending a minute on. there are two questions, right? Can you solve that problem off-chain given a good computer in the loop structure where you're being fed the data quickly enough, you solve your problem quickly enough for your users, then you send your transactions quickly enough on chain. So that's one thing. This is good. This is useful. But it's actually, like we said, a bit front run. So you find out that it never really works as well as it should. You're being stolen away some of the value that you think you have, and there are defensive measures, but essentially you're kind of being screwed at the moment. It would be so much better if you could actually run that optimizer on chain, so that the optimizer is actually moving the numbers with in the context, in the exact context in which you want to solve the problem. And at this stage, once this is happening, there is no discrepancy, there is no asynchrony, you're in instantaneous computing conditions. It will take a little bit of time to optimize, but nothing moves of the state of the system. Therefore, you have actually optimal answers, I mean, up to a precision. So an outcome of this work is that we know how to split optimally on chain in simple conditions with closed formulas, so we don't do too much calculation on chains. It's perfectly viable, but we don't expose ourselves to being front run because we're running our algorithm off chain. So yeah, we can in special conditions we can do it very mathematically and efficiently.
So there's a question by Dan Merkel. He's asking whether your arbitrage experiments is taking into account gas costs, and if so, does playing more gas can influence the result?
Yeah, so this is a very good question. So as soon as you send your arbitrage solution, so you solve your arbitrage problem off chain, as soon as you've solved it, you send this as a batch of transaction that you want, or I mean, there are two ways to do it, actually. Let's say it's a triangular arbitrage. You can send your 3 transactions in a row and ask that they're executed atomically, one after the other, which is key. But or you can talk to a smart contract which is already on chain and just communicate with some kind of private language to the smart contract, so that the smart contract will actually execute online directly on the chain the same thing. So semantically they're the same, but in practice they're super different, because when you send in the clear in what people call the mempool, which is the public places where transactions are waiting to be incorporated in the next block, when you send them, everyone sees them, and so bad players actually will see them. And for simple TriState machines, it's totally trivial if you're given the opportunity to steal the arbitrage or to manipulate the actual if you're the master of the order in which the sequence will execute, if you can intervene before and after at your leisure, then you can make money with no risk. So now you have to pay for doing this kind of thing. And so one way for the persons who want to do the arbitrage to escape from the predatory actors that are going to pay really high to front run them is to pay themselves a lot of gas. And I don't know if you're familiar with this, but on Ethereum, being first, I mean, the expectation is that the miner run algorithms whereby they take the people who are bidding the highest on the gas price, so are ready to pay more. So you can enter that competition. But if you lose it, you lose, not only you don't have your arbitrage, but you've left your bid. So that happens. And so that paper, that Swiss paper I was referring to, they actually see that. They see that if you do it like that, it will work, I think, I think 1/3 of the time, not more. And the other times you'll have paid for nothing. If you do it with a smart contract, it's a little less obvious for bad players to see what you're doing, and it works 2/3 of the time, I think. So yeah, these are very concrete questions. we've not done it in the maths, but it seems really difficult to model seriously the adversarial behavior of the bad players, right? So it wouldn't be a very substantial theoretical problem to solve, but it would be practically interesting, and that's certainly what they are doing.
So thank you, Vincent. We are having a pretty savvy audience because there are questions about sandwich running now. So I will let you interact with Massimo offline because we need to stop the YouTube stream. So if you have some time to stay with us, we will have a time for informal chat with Vincent. But otherwise, thank you for your participation. Thank you, Nick, for setting this up as usual. And see you next time for the next GReTA meeting. And let's thank Vincent again, even remotely. But thank you very much for the presentation.
Thank you.
And stay with us for informal discussions right now.
Yes, so then just say, I'm going to stop the YouTube live stream now. To everybody on YouTube who wants to join us, there's a link in the chat, so you can just come online into the meeting